Um, I'll get some more copies. You mind giving her one, Rose? Okay, so it's actually not a unit circle. It is a coordinate system for polar coordinates, which is what we're talking about today. I'm going to go get to the math lab and get some more copies. Everybody should have one, though, and we're going to use it to help us plot points in the polar coordinate system. Okay, so polar coordinates are just another system. We're used to this system, right? With the x-axis and the y-axis. And we know to get out to some point, if we have a point, say there, to get to that point we have to go out by x and we have to go up by y. Are we all right with that? So polar coordinates allow us another way to get to that point. Rather than going out x, up y, we extend out a distance of r. And the reason why we choose r is r stands for like the radius, okay? So we're going, r is defined as the distance you are away from the origin to your point. So it doesn't have to be a horizontal distance, it doesn't have to be a vertical distance, it's the distance from the origin out to your point. But now you need one more variable, because like if I want to describe that point, yeah, I can say I got to go a distance r, but I got to know where that r is. Is that r right there, or is it right here? Or is it right here? And the second variable that comes in is theta. So, and theta is measured from the positive x-axis. It comes from here and it wraps around, just like you would with the unit circle. So, we're going to define theta as that. So let's write what I just said. R is the distance from where to where? From the origin to point xy. And then theta is the angle measure in radians. Those of you like degrees, I'm sorry. In radians from the positive x-axis. You guys know what I mean by positive x-axis? There's negative and positive, right? So it's the right side. Positive x-axis to r. Okay, any questions so far? Okay. So the very first thing I want to do is I want to talk about how we then use those two definitions for r and theta to plot points. So when you have a point given in polar form always looks like this. It still looks like an ordered pair, but instead of xy like we're used to, it's going to be r theta. So r is always the first one, theta is always the second one. So when you see here, that means r is 3, theta is pi over 2. And everybody should have in front of them a polar graphing coordinate system that looks something like this. You can, if you have any, I'm going to go out and get some more, so when you guys work on your lab today, you can plot on this and attach it to your lab. But there's more of these in the math lab. You can also find them for free on the internet. I just pulled this one off the internet. So what was our first point? Our first point was 3 pi over 2. So we start at the positive x-axis, we move pi over 2 away from that, and that takes us up to 90 degrees, right? And then we go, how long is r? r is 3. So we'll come around pi over 2, and then 3 is going to be 1, 2, 3 right there. So that point right there would be 3, comma, pi over 2.
Would every graph like this be the exact same, like units away from origin, or does it change?
I don't understand your question.
Is it like each circle on that, is it like the x coordinate? Like it always can be that distance away?
Distance away from what?
So when we have it on the graph, our x coordinate is going to be the distance away. We move on that.
On the x-axis?
Yes.
Yeah.
Are these lines the same concept that?
Yeah, kind of. So like the XY axis could also be on this graph at the same time. Let me change colors here. So this is still right here. Oops. So this right here is still the x-axis. This right here is still the y-axis. And each one of these little, where the circle goes around, this circle, this first inside circle represents at every angle a distance 1 away from the origin.
Okay.
But on the xy axis, this right here, where it touches here, would be 1. This would be 2.
Okay.
And likewise on the y-axis, this would be 1. This would be 2. And this would be 3. So what's the equivalent? This point has an equivalent xy coordinate. What would it be?
0, 3.
0, 3. Does that make sense? This is the same. This is the same as 0, 3. And one of the things we're going to learn about today is how to convert between here and here and between here and here, back and forth. That's actually the first two concept questions. What formulas allow us to convert between polar and Cartesian, and then vice versa. Does that make sense? Okay?
That was
Did I answer your
that
question?
was what I was looking for. Yeah, like
Okay.
if it was the same thing around. Okay.
Absolutely. All right, what's the next point?
-1 pi over 3.
-1 pi over 3. Now, anybody, okay, first of all, pi over 3 we know is right here, right? Pi over 3. Now, anybody have any ideas about -1? How we would deal with that? R is -1. What do you mean by go the other way? You go the opposite direction, yeah. So pi over 3 puts us on this ray right here, right? Puts us on that. If we go -1, we're just going to go, and we're going to continue on that ray, but we're going to go in the opposite direction. So it's going to look like that. It's going to be right there. That would be -1, comma, pi over 3. Now, -1, comma, pi over 3, one thing I want to say is that no two, man, the sickness is still with us. I started it yesterday. Everybody's throwing calculators. Show love to your calculator. Everybody make sure it's strapped in and secure. Okay. Okay, so one thing I want to say about polar coordinates, no 2 points are unique. Okay? There's not one unique description for that point. Can anybody think of another way I could define that same point? A different r and a different theta. 1, comma, 4 pi over 3. You guys see where that came from? Everybody agree with that? 4 pi over 3 takes us around to here, and that's a radius of 1. Yeah. How about another one? What do you think of another one? Michelle? 1/10 pi over 3. Yeah, if you add 2 pi to this, it takes you all the way around and puts you at 10 pi over 3. You just take another time around. So yeah, this is equal to 1, comma, 10 pi over 3. That's If you take this and you add 2 pi to it, you get 10 pi over 3. Anybody else? You think of another one? That's the one I was thinking. That was the other one. There's an infinite number of these, but yeah, how about 1 comma negative pi over 3? What does it mean if we make our angle negative? Elijah? Yeah, instead of going counterclockwise, we go clockwise pi over 3, which takes us to right here. Questions? Okay. So what I'd like you to do is take those, 3 more points or 2 more points, and go ahead and try to plot those on your own if you haven't done so already. These, yeah, C and D. Try to do C and D on your own, please.
Thank you.
What did you guys notice about C and D?
They're at the same.
They're at the same point, right?
Yeah.
Did it disappear?
No, it's
I saw the point go there, it disappeared. You guys see where Rose put the point before it disappeared? Did it disappear?
No.
Was it not there?
I don't know.
I don't know what happened. Well, I saw it be there. She put it right here. Yes? And that is actually both points, isn't it?
Mm-hmm.
That is the point. What was the first one? It was
-2,
3 pi over 4, which is equivalent to +2 negative pi over 4. They both describe that same point. All right, so everybody all right with that part? Bless you. Sneezes are contagious. Throwing calculators is contagious. 'Tis the season for allergies. All right. Does anybody have any questions so far? We all right? Okay. Let's go back to our. Oh no! Just flew on me. Forgot that I can't drag like that.
Oh, that sucks. I don't
All right, so this axis that was here in your notes, that was to put those points on, but you guys have that nicer one to plot on. If you want to add them to that, you can. All All right, so let's talk then now about how we actually convert. How do we convert between x, y, and r theta? So here you have your xy coordinate system, right? There's your x-axis and your y-axis. You have a point here which can be defined by xy, but that same point can also be defined by r theta, where r is this distance and theta is that angle. Okay, so anybody have any ideas for how we could convert between the two? No tricks though. No tricks though. I mean, it's going to involve trig. Yeah, Michelle? Yeah, that's close. So we've learned before that x, like on the unit circle, x is related to the cosine of your angle, y is related to the sine. The only thing that's a little bit different is in the unit circle, we assume that the radius is 1. In this case, the radius is not always going to be 1. So we know from right triangles, trig of right triangles, that the cosine of theta would be equal to what if we were looking at this right triangle right here, which is what we did in trig. Is that right, Eddie? Yeah, so if I look at this right triangle, how can I define cosine theta if this is my theta right here? You can tell me what ratio. Stefan? X over R. Everybody all right with that? No, cosine is adjacent over hypotenuse. Okay, so if I wanted to then solve for, what do we want? We want x, right? If I wanted to solve for x, how would I get x by itself? Times by r, yeah. So if I multiplied by r and multiplied by r, those r's would cancel, and I would get that x is equal to r times cosine theta. R times cosine theta. And likewise, in the same way, if I took the trig ratio for sine theta would not be x over r, it would be y over r. And you could solve for y, and you get y equals r sine theta. Good? Any questions? Okay. So that's how, if you have, are these two formulas going to help us convert from polar to Cartesian or from Cartesian to polar? Well, you're plugging in r and theta to get x. Yeah. So these ones here are for polar to Cartesian. All right. Okay, and then there's formulas for going the other way. These other formulas, we haven't talked about what they are yet, but those formulas are for going from Cartesian to polar. Bless you. Okay. So, what's x squared plus y squared equal to? It depends on what r is. Yeah, it's r squared, right? It's Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. R squared. It could be 1 if r is 1, right? And then tangent theta. How are we going to get tangent theta? Tangent theta it's another trig. It's y over x. Do you have any Any questions? Okay, so I think you guys could probably do example 1 there. Okay, can we convert from this is in polar or Cartesian? Polar. Can you guys convert that to Cartesian real quick? What do you have to know? Because you're going to have to take the cosine and sine of 2 pi over 3. You guys remember what cosine and sine of 2 pi over 3 are? Maybe. Well, you might have to exact that. Not just the cosine. So you're going to need to know what cosine is. So we need a little review of unit circle. All right, so if I have a unit circle, I can tell every angle from knowing the first quadrant. This point here is 1, 0. This point here is 0, 1. And then I have 3 points in between here. I have one at pi over 4. I have one at pi over 3. And I have one at pi over 6. At pi over 4, we have this triangle. And with that triangle, the x and the y are equivalent. Everybody agree with that? It's a 45, 45, 90. The x and y are equivalent. And that's the one where the x and the y are the same. They're both root 2 over 2. Now, the other 2 points are either, this is how I remember it. Honest to God, this is how I remember it. One of them is 1/2 root 3 over 2. And one of them is root 3 over 2, 1/2. Is this coming back? Okay, this is how I remember it. This is what I think in my head every time. Which one of these numbers is bigger, 1/2 or root 3 over 2? Root 3 over 2 is bigger. So, in which one of these points has a bigger y value? Pi over 3 does. So this has a y value of root 3 over 2 and a smaller x value of 1/2. Whereas pi over 6 has a bigger x value, root 3 over 2, and a smaller y value. So the points go like this. This would be 1/2 root 3 over 2. Anybody ever thought of it that way? Yeah? That's how Stefan thinks about it, yeah. To me, it's an easy way to remember it. Do you like that? Yeah? Okay, so once you know that, you know every single other point if you know where x's are positive and negative and y's are positive and negative. So what is our angle? 2 pi over 3. So So we know that this is at pi right here. And if you split it into thirds, this would be 1/3, and then this would be 2/3 right here, 2 pi over 3. And so this is the same exact point. It's 1/2 root 3 over 2. That's the same point as that one, right? The only difference is that one of them is negative. Which one is negative? X is negative. Because to get out to this point, we have to go to the left. We have x negative, y is positive. So it's a negative 1/2. Questions? So if we're going back to that problem we just looked at that required us to do cosine and sine of that angle, remember x is the cosine and y is the sine. So if I want to do this, I know that x is equal to r cosine theta, which in this case is 6 times the cosine of 2 pi over 3. And we just reviewed that the cosine of 2 pi over 3 is negative 1/2. Everybody all right with that? So this is 6 times negative 1/2, which is negative 3. Likewise, y is r sine theta, which is 6 times the sine of 2 pi over 3, which is 6 times what? Root 3 over 2. Two goes into 6 3 times, and we get 3 root 3. So my answer, if I put it in polar coordinates, the x is negative 3, and the y is 3 root 3. Anybody have any questions? Good? Okay, let us move to the page 100 here. Let's go the opposite way. Let's convert negative 1 back to polar coordinates. You need the other two formulas, right? Go ahead and see how far you can get with that.
Then our so maybe go to two, right? So our formula for the root two is 5 times. Scott got you good. My favorite is 5 times.
So I don't. I gotta put my calculator on here. I don't have it on right now, but all right. So what formula do we use to find r? Yeah, x squared plus y squared equals r squared, and we know that x is -1. We know that y is also -1. So that means r squared is equal to 2, which means r is square root 2. Actually, plus or minus square root 2, but typically we're just going to take the positive one. Okay, and then on the opposite side, we know that we have that other formula, the tangent of theta is equal to y over x. So tangent theta is equal to -1 over -1, which is +1. And there's two ways you can think about this. So one way you can think about it is what angle theta gives the tangent of 1? Well, the only way to have tangent be 1, remember tangent is sine over cosine. So if you go back to our unit circle, which angle is the sine and cosine going to be the same? Pi over 4, right? So at pi over 4, sine and cosine are both the same. So when you take sine over cosine, you get 1. So the angle's got to be pi over 4. Now there's one problem with that though. Does anybody know what the problem with that is? Yeah, so they are also the same in the third quadrant, because in the third quadrant we get the x is negative and the y is negative. Here, like in the second quadrant, x is negative, y is positive. So when you divide y over x, you get a -1. We don't want a -1, we want a +1. So we need them both have the same sign. What's this angle? 5 pi over 4. Now how do we... So we have pi over 4 and we have 5 pi over 4. How do we know which one? How can we be sure about which one? Stefan. The point was -1, -1. Right? Which quadrant is that in?
Third.
It's in the third quadrant. That means our angle has got to be the angle that's in the third quadrant. So we're going to... jumped on me. So we are going to throw out this one. This will be our answer right here. Now, just did it to me again. Now if you want to use another approach to find theta, oh my goodness, I got to stop touching that. Sorry about that. Technology can be good and bad. we could also say that theta is equal to the inverse tangent of 1, and you can do that with your calculator. Yeah? Now the calculator, if you're in radians, it's going to give you like 0.78 or something like that. It's not going to give you pi over 4. But what some people will do is they'll put their calculator in degrees mode. And if your calculator's in degree mode and you take the inverse tangent of 1, it gives you 45 degrees. And if you know that 45 degrees is pi over 4, that's another way to think about it. Does that make sense? Okay? So our answer then is our point is, what comes first, r or theta? R comes theta, R comes first. And then my angle, 5 pi over 4. All right. You all right? I alluded in yesterday's class that this is going to be used a lot in Math 70. It absolutely is. No. Yeah. You're going to use this a lot. This system is not really too complicated, but you need to know how to work with this. And so a lot of the beginning of this class, as you can see, we're just working with how do you operate under this system. The next part that we're going to do after the break is we're going to start talking about graphing and how do we graph. What if we have a curve, what does the graph look like? Now, before we take a break, though, I just want to consider one graph, just to kind of start thinking about this. And that is, what if I have r equals 4? Do we have any ideas about what that equation is going to look like? Notice, does it say anything about theta in it? No. Now, one of the things you have to start to learn about graphing, and we've already seen this before in the Cartesian system, when we have like x equals 2 or y equals 3, this equation doesn't involve y. There's no y here. And this one has no x, right? Whenever you are missing one of the two variables, that means that that variable that's missing can be anything. So here, y can be anything, and here x can be anything. Which is why the graph of this, x equals 2, is a horizontal or a vertical line? Vertical line. It's a vertical line that goes through 2. This is x equals 2. And notice, every point on this line, x is equal to 2. For example, right here, this is 2, 2. X is 2. X is 2. But y can be anything. Right? We're not defining y, which means y can be any point. But no matter what point it is, x has to be 2. So what are we saying here? We're saying r has to be 4, but theta can be anything. What's the graph of that one look like? It's a circle. It's a circle. Because remember, we're dealing now with this system. Uh-oh. It's not allowing me to go, but we're dealing with the polar system now. And so what we're saying is 1, 2, 3, 4. We're saying at this point would be 4, 0. This point would be 4, pi over 4. This would be 4, pi halves. And so any point around a circle of radius 4 is going to be a radius 4, a distance of 4 away from the origin, but theta can be anything. Okay? All right? All right, let's take a break. We'll come back at 9:01. 9:01. Thank you. Huh?
I found the polar mode on the calculator, and then started plugging stuff in.
So it does colors?
Yeah. Pretty cool.
Okay.
Now you can say.
Hi, Corey.
Okay, so we are going to move on here. We're going to talk about graphing. Now, just to show you that a lot of this graphing can be done with a calculator, just like we did yesterday with parametric equations, we can do this with polar. So I have my calculator up here, and we need to again change the mode. So you're going to want to go to mode, and notice you can go down to, there's parametric, but then the third option is polar. So you want to go ahead and highlight polar. And then once you do that and you go back to y equals, you will notice now that it's not xy anymore like we had with parametric anymore. It's now r equals. So anytime you want to graph on your calculator in polar form, it has to be in the form r equals. If it's not r equals, you're not going to be able to put it in there. Just like with xy's, we got to have y equals to put them in here. For the calculator, it has to be r equal. So, for example, we just talked about r equals 4 is a circle with radius what? 4. So you can put that on there. R equals 4, and you can hit graph. And there you go. All right. So my window goes from 0 to 2 pi for theta, and then I have negative 10 to 10 for all the other ones.
Can we change the?
It's still not going up. What was it? Great.
Good job, Tim. Good deal with you. Try your CIA minutes.
Sorry, go back to the graphing it. Well, what was thinking is like,
Oh, I put it in there. I don't know why it's not graphing. That's strange.
Is it in degrees or radians?
Oh.
that's probably why, because I changed it.
Good job, Tim.
Thank you, guys.
That just happened to me.
Yeah, make sure your calculator is in radians.
Radians. We're just making new stuff up as we go, guys.
All right, so look at this next one. Find the Cartesian equation for r equals negative 8 cosine theta. Now, does this look at all familiar to anything we've done lately? I mean, when we have cosine, it kind of makes us think, like yesterday we had x equals r cosine, remember that? And that was part of our parametric equations for a circle. Part of this wants me to think it's a circle, but we don't really know yet. Now, notice the directions. It says find the Cartesian equations. That means I need to, it's currently in what form?
Polar?
It's currently in polar. So that means we're being asked to go from polar to Cartesian. Now think about what our formulas are for that. Our formulas are, if we want to go from polar to Cartesian, we have what? Or actually, I mean, we can use any of the formulas. It just kind of depends. But think about the ones that we have. We have x equals r cosine theta. Y is equal to r sine theta. And then the other one, we might be able to make use of this one too. 'Cause this one really, if you think about it, it goes both ways, right? If you go this way to this way, it's one, but if you go this way to this way, it's the other one. So, are any of these, or parts of these, in this equation right now? Cosine, but what's missing over here? We have cosine, but we're missing r.
That is R.
What? Well, r's over here, but we don't have r over here. We need r over here. How could we get r over there? If we're going to use some of these formulas here, we have to be able to get parts of this equation to look like some of these. Yeah, Eddie.
Can't you just divide by -8? And then,
You could, but that's still not going to get you r cosine. It's going to be r equals cosine. We need, remember, we need r cosine, right?
Excellent.
It's not r arc cosine, it's r cosine.
So we can do it
It's not going to help us. Because if you have inverse cosine, it's going to give you inverse cosine of r is equal to 8. Does that help us? Not really. What can I do to this equation to get an r in front of cosine? Multiply by r, yeah. I think you guys are thinking it's harder than it is, yeah. That's all we're going to do. We're just going to multiply by r.
I didn't think we could do that.
Yeah, you've only done it since Algebra 1. Multiply both of the equations by something, right?
I meant like just throw random extra variables. I didn't know how to do that.
So the left side becomes r squared, right? And then the right side becomes -8. And I'm going to go ahead and put the r in here just so we can see it the way we want to see it. Is that all right? Okay. So now, look at that actually helped us on the left side too, didn't it? Because the left side now looks like what?
That's what
R squared, and we know that r squared is equal to, yeah, so on the left side we can write x squared plus y squared. And then on the right side we now have -8, and then r cosine is equal to x. Are there any more r's and thetas in our equation? No. So it now is in Cartesian form. We still don't know exactly what it is, but we learned on Monday, what do we have when we have x squared and y squared? It is a circle, yeah. Now, one of the forms of a circle, the ones that we talked about yesterday, is when they're centered at the origin. We know that x squared plus y squared is equal to r squared. That's the equation when the center is at 0, 0. But my hand is hitting that sidebar over there. Okay, but there's many times when the center is not at 0, 0. So we have an h. Okay, does anybody remember what that formula looks like? Eddie?
Isn't it x squared minus h?
Close. X minus h squared plus squared equals r squared. And so to see what the center actually, the circle actually looks like, we need to get it in that form. So anybody have any ideas for how we could do that?
Honestly, it's like move the AX over to the other side.
All right, so we move the 8x over, we have 8 squared, x squared plus 8x plus y squared equals 0. Still doesn't quite look like this form over here, though, right? What can we do to get it in that form? Add 16. Complete the square. Yeah, so if we add 16 here, now if we add 16 to one side, we also have to add it to the other side. So this actually becomes something right here that's factorable. It factors to x plus 4 squared. It's now a perfect square. Then we still have the y squared on the end. You guys see what we did? This is called completing the square. If you don't remember that method, the way you figure out what number you need to add here to make this a perfect square is it's always this number. You take half of it. Half of 8 is 4, and you square 4 is 16. If you got 16 here, you got to add it over there. So we can now see that, yeah, this is a circle. It now has this highlighted form over here, doesn't it? What's r equal to? R equals 4. Circle with radius equal to 4. And what's the center? Negative 4, 0. In other words, h is negative 4 and k is 0. All right, does anybody have any questions? Shall we try with our calculator, verify this? Pull open your calculator, go to your polar equation, and let's put that equation in. Make sure you use the negative button, not the subtract button. So negative 8 cosine. And now notice again, just like last time when we were in parametric, when we hit this button it gave us a t. When we're in polar it's going to give us a theta. And when you hit graph, does that look like a circle with radius 4 and a center at negative 4, 0? Absolutely. I think that's pretty cool. Math works. Because math is cool. All right, your turn. Find the polar equation for 5x minus 3y equals 15. Find the polar equation for 5x minus 3y equals 15. There's nothing fancy to do on this one. Square it like that. Can you square both sides? This square. So algebraically speaking, is this legal? If I have x plus y, if I have x plus y equals 6, can I say that this is true? No, you can't. For example, if this is 5 and 1, then this would be 25 plus 1. Is that equal to 36? No. And you can square both sides, but squaring both sides means you do that, which is not equal to x squared plus y squared. It's equal to x squared plus 2xy plus y squared. And there's no need to get the x squared and the y squared. You already have a conversion. You already have a conversion for x and y. It's just you plug in. It's just 5 times x, but x is what? X is r cosine theta. And then minus 3 times r sine theta equals 15. Okay? Bless you. And that's it. Now we could try to solve this for r. Could we solve it for r? What would we have to do? You could factor it out. So if you factored it out, you'd have r times 5 cosine minus 3 sine equals 15. And then we could divide. So r equals 15 over 5 cosine theta minus 3 sine theta. And you could again put that in your calculator. We're not going to do that with this one, but I believe WebAssign will take this form right here, though, if I ask you that question. Okay, does anybody have any questions? Okay. Now what we have right underneath here is a bunch of common different types of graphs that you're going to see with polar. Now let's go back to this conversation here. Remember when we had one variable and one variable was missing and it was equal to a constant, we allowed the other variable to be anything? So when I say theta is equal to something, the example of this might be theta equals pi over 4. What does that say about r? R can be anything. So that's going to give you a line. It's going to give you a line. If theta equals pi over 4, pi over 4 is this line right here, right? Any point on that line says, if I take any point on that line, that means r can be anything, but we're always on that line because we're not allowing theta to change. Theta is always pi over 4. How about vertical lines? Vertical lines look like this for us. Okay, either r cosine theta equals a constant. The horizontal lines look like r sine theta equals a constant. Circles can be some of these forms. We already did one of these over here, right? Example B, or example 3, I mean. Example 3 was r equals negative 8 cosine theta. That was just like this, right? So this is a circle where the center is where? Where's the center? This is like the first one we did, like r equals 4. Where's the center of that one? Origin, yeah. So with those type, the center is at 0, 0. But what did we learn about these other types? Is the center, like that one we did up above in example 3, is the center at 0, 0? No. So center not at the origin. And then there's all kinds of different other shapes. Let's get an idea for what these other things look like. So if you have a cardioid, cardioids have the form a plus or minus a cosine theta. So let's pick an a. Somebody throw out an a, some constant. 2. All right. So if we graph that, let's do 2 plus cosine plus 2 cosine theta. Let's graph that. Let's do 4. 4 plus 4 cosine theta. See the shape of it? It's not an ellipse though, because let me turn off the inside one. See how it kind of comes back to the origin? Comes around there. What about if I change it to a minus? What about if I change it to sine? It makes it go along not the x-axis, but the y-axis. So can you picture what it's going to be if I make it a plus now? If I make this a plus, okay. So that's called a what? Cardioid. Okay. You also have limacons. Limacons are a shape when you have now 2 different constants. These aren't the same, but they have now become different. So if I change this, for example, to a 2, notice the difference. It doesn't go back to the origin. It's kind of like a funky looking kind of circle thing. That was good mathematical terminology there, a funky looking circle thing. But my favorite are roses. The very last option, and you can play around with these to try to get whatever you want. But if I do a rose, for example, if I do 4 times the cosine of 2 theta, we get a rose. Okay. Now, I can make the rose bigger by changing the a. So if I change this to like a 7, for example, instead of 4, I get a bigger rose. What do you think changing the other number is going to be? What if I change the n? Any ideas? Yeah, Elijah. So it does have to do with the petals. It's not necessarily, it's kind of wider and narrow, but it actually makes more of them. So if I go y equals, and I change this to like a 4, you didn't know you were doing art today, huh? So, I mean, they call it roses. I mean, it looks like a flower petal, doesn't it? Or doesn't it kind of look like some sort of flower? Right. So any questions about that? It is pretty cool, yeah.
So if it's like an even number, it would be like the roses, and if it's odd, it would be like the same number? Or?
Well, let's play around with that. So what did we just pick? We picked, what was n equal to there? 4. And we got how many petals?
8.
We got 8. And what did we get when n was equal to 2? 4 petals. Let's do an odd number now. Let's make this a 3. How many petals there? 3. How many petals do you think it's going to be if it's a 5? 5 petals. So, odd numbers for n give you n petals, but even numbers for n give you twice n.
Yeah. I didn't realize that.
All right? Okay, any questions?
The petals are like separated, is it 360 divided by 9 or something?
How the angles? Yeah, it kind of has, yeah, so there's going to be, I don't want to get too much into that today. We're going to talk about actually next class. When we talk about, next class we'll learn about how to find the angle, or the area, say, inside of one of these petals, and we'll talk about how the angles work and stuff. I don't want to get too far into that today, but yeah, you're on the right track.
Oh, heck no. Just looking at that, I'm like, no way.
All right, so
I did.
let's jump over to the last page here.
I like this. That's cool.
Last page. So the last thing we're going to do is just like we did in the last class where we found the equation of a tangent line. We are going to do that, but we're going to do it for now polar, and it is very much related to what we did with parametric equations. Remember this formula right here? dy d theta over dx d theta. That looked like what we did last time. Remember we said dy dx was equal to what? Yeah, this was on the quiz today, right? dy dt over dx dt. So we're basically going to use the same formula, except it's not in terms of t, it's in terms of theta. And we have to remember that R is a function of theta. So when we're taking dy d theta, when we're taking dy d theta, we're taking the derivative of y. We're taking the derivative of y with respect to theta, and y is r sine theta. Right? Y is r sine theta. This is y. And remembering, right here, r is a function of theta. So we have a function of theta times sine theta. That's a function of theta times a function of theta. What rule do we need? Chain rule. No. The product rule.
Oh, God.
Function times a function, we need a product rule. So this is going to be, if I take its derivative, it's the first times the derivative of the second plus the derivative of the first times the second. Yeah? And then likewise, if I took dx d theta, I'm taking the derivative with respect to theta, not of r sine, but of r cosine theta. And if we apply the product rule, again, this is going to be r times negative sine theta plus r prime times cosine theta. And so, if I look at this formula right here and take this is my dy d theta and this is my dx d theta, this is really the formula right here. This is equal to dy I'm running out of gas with my pen here. It doesn't want to write. I think my battery's dying. Okay, so that's my formula. And this is, how do we find the slope of a tangent line using polar coordinates? This is how you find the derivative. You take the derivative of y with respect to x, you do that. Okay? So, determine the equation of the line, tangent to the curve, determine the equation of the line tangent to r equals 3 plus 8 sine theta at theta equals pi over 6. I want to find dy dx, which means first of all I need to know all those derivatives, right?
Would you leave that that r times negative sign? Would you just leave it like that, or would you make it negative r sign?
You can make a negative r sign. I just,
It's a bit better.
yeah. All right. So I'm just following this. R is 3 cosine, not 3 cosine. R is 3 plus 8 sine theta times cosine theta plus r prime. R prime would be 8 cosine theta times sine theta. You guys see where I got that from? I'm following this formula. So R is right here. This is R. 3 plus 8 sine theta times cosine theta plus r prime, the derivative of this, the derivative of this, the derivative of 3 is 0, and the derivative of 8 sine theta is 8 cosine theta times sine theta. So can you guys fill in the bottom then, this part? Yeah, most of the time, the way this is actually written is like this. It's r prime sine theta plus r cosine theta over r prime cosine theta minus r sine theta. That's the way you'll most of the time see it in books. Everybody agree though that's the same thing? Let's move it around. All right, so who can tell me what's the bottom? What do we got? Elijah. Yeah, because it's cosine theta times cosine theta, so you'll get cosine squared, right? All right. So what do we do now? Plug in theta, pi over 6. Yeah, so this is going to be 3 times 8 sine pi over 6 times cosine pi over 6 plus 8 cosine pi over 6. I'm running out of room. Sine pi over 6 over negative 3 plus 8 sine pi over 6 sine pi over 6 plus 8 cosine squared pi over 6. And you just need to know your right triangle. So this is 3 plus 8 sine of pi over 6, 1/2. Cosine of pi over 6, root 3 over 2. Plus 8 times root 3 over 2 times 1/2 over negative 3 plus 8 times 1/2 times 1/2 plus 8. Cosine of pi over 6 is root 3 over 2 squared. How are we doing? You guys get the point? So 8 times 1/2 is 4. 4 plus 3 is 7. I think this is 7 root 3 over 2 plus 2 root 3 over negative 7/2 It's plus 18. This is 11 root 3 over 2. Over 29 over 2. Root 3 over 29. What's that? The what?
God.
That's 8. Right here. When you square root 3, you get 9. Oh, I made a mistake. You're right, it's not 18. That's not 18. That should be 3 over 4 is 2. I think 6. 6. Which makes this 5 halves. Which makes that 11 root 3 over 5. How about that? Just algebra if you plug it in. So that's the slope, right? The derivative tells us the slope. Any questions so far? Yeah. Well, 8 times 1/2 is 4. 4 plus 3 is 7 times 1/2. 7 halves. That's algebra. That's the algebra. Maybe too much algebra. We're almost ready to take a break. What do we do now then? Because we didn't just want the slope. That's m, right? What else do we need though? We need y equals mx plus b. We need a point though. We have theta as pi over 6. So we do it. Yeah. What's r equal to? 3 plus 8 sine pi over 6. Sine of pi over 6 is 1/2. So we have 3 plus 8 times 1/2, which is what? 4 plus 3 is 7. So x then is equal to 7 times the cosine of pi over 6, which is 7 times root 3 over 2, which is 7 root 3 over 2. And then likewise y would be 7 times the sine pi over 6, which is 7 times 1/2. So this is actually a case where I like to use point slope form, because I have y minus 7 halves is equal to 11 root 3 over 5 times x minus 7 root 3 over 2. I'm going to stop there.
That's it?
You could multiply it out and add that terms. I don't think we need to spend time doing that. So you got to find the point and you got to find the slope. Okay? Questions? Okay, we have a lab. 10.3 lab.